Okay, hello and welcome everybody to the next event in our webinar series, a presentation by guest speaker and personal friend Dawon Bonneville from the Integrated Optical Systems group at the University of Twente. So Dawson and I go way back. We had labs in the second floor basement of one of the buildings on campus at McMaster, a couple rooms apart. So we definitely collaborated on a lot of fun experiments. I'm interested to see sort of what new and exciting stuff has come up since you've departed. Okay, so Dawon Bonneville received his bachelor's degree and PhD from McMaster University in engineering physics, specializing in integrated photonics with a variety of materials for amplifiers and sensors. He's now a postdoc in the Integrated Optical Systems group at the University of Twente in the Netherlands. There, he continues his research and is active in industrial collaboration on integrated photonics with a focus on sputtered deposited aluminum oxide for UV photonics, as well as erbium-doped alumina for amplifiers and lasers. Throughout this talk, please feel free to submit any questions you have using the Q&A tool. Dawson will be answering any questions at the end. As a side note, I'm noticing a lot of similar colleagues from McMaster within the same groups that we were in, so I'm hoping for a lot of good questions coming from them especially. And now I'd like to hand the talk off to Dawson. So Dawson, take it away.
Thank you so much for the kind introduction, David. Before I hop into it, I read online that it's nice to start a talk with a fun fact. So a fun fact, my wife and I had our 13-week scan today for our pregnancy, and I learned that babies do not have kneecaps. So you can all walk away with at least that fun fact, if none else. So as David mentioned, my name is Dawon Bonneville. And today, as you can see on the screen prompted in front of you, I'll be talking about aluminum oxide waveguide technology, diving into a brief history, and of course, the future perspective for integrated photonics. And you can see here I share a nice author list with some of my colleagues here at the university. I'd like to give a special shout out to Carlos Osorio Martinez, who has been a pivotal member for a lot of the research that I'll be presenting you guys with today. So let's hop right into it and waste no time for the fun stuff. So brief introduction, you already heard a little bit about it, so I'll breeze over it, but who am I? Why do I care about this so much? And why do I think this is a super neat material for integrated photonics? I'll do this by highlighting and comparing it to a couple other heavy hitters and big names in integrated photonics, what makes aluminum oxide stand out, and what kind of shows its prowess for the future in integrated optics as a whole. So as David mentioned, for about 6 years, I had a research career at McMaster University under the supervision of Jonathan Bradley, where I was lucky enough to do my PhD with very bright individuals. Some of them now work at Thorlabs, and many across the whole world in integrated photonics, where I did a dissertation on low-cost and versatile fabrication of silicon-compatible photonic integrated circuits for active devices and sensors. And now for the last almost 3 years and a quarter, I've been at the University of Twente doing similar research on what we're going to talk about today on aluminum oxide. But this kind of full shows that I'm now 30, and for almost 1/3 of my life, I've been working on aluminum oxide waveguide technology. So it's very near and dear to my heart, and I'm very passionate about the material, which I hope will reflect in the talk that I'll give for all of you guys today. The Integrated Photonics at Twente has a very diverse and active ecosystem, many working in different areas or paradigms of the technology. Whether at the core of it, you see a lot of material research on sputtered waveguide materials, with Sonia's face popping up there, my supervisor at the Integrated Optical Systems group, along with another assistant professor, Lantian Chang, next to her, doing 3D wafer level integration technology. But there's a whole load of research that goes on here in our clean rooms into other materials for integrated photonics, whether it be transparent conductive oxides or actually how to fabricate these materials. And if you step into this other device section, you can see that the Integrated Optical Systems group covers quite a bit of it, whether it's for applications in LiDAR, early disease diagnostics, data and telecom, which we should actually start to circle ourselves in now as well. Or on the left, a lot of heritage in quantum technology from other professors here. And on the right side, you'll see David Maripong, a researcher who does quite a bit into acoustic waveguides and stuff like this. So integrated photonics is a very rich ecosystem here at the University of Twente, and we're happy to be part of a larger consortium of many exciting researchers who get to explore the topic in various ways. We get to explore this topic in various ways because we, at the heart of integrated photonics, of course, is fabrication, and we have access to a lot of fun and interesting tools and equipment here at the Mesa Plus Nano Lab, which is located right on University itself. So see that nice big red building, a standalone nano lab, which has 1,250 meters squared of clean room for specialized equipment, whether it be thin film deposition using PVD or CVD, which we'll talk a little bit about today. It has mass lithography, electron beam, tons of etchers, lots of dicing, and of course, a whole lot of characterization equipment to do a whole lot of analysis on the materials. And I'll present to you guys our results on aluminum oxide in the past and present that we've been getting. Of course, you can see here a lot of the research areas for clean room can be diverse, but I'll be talking about photonics today. So photonic integration, for those who have less of an experience on it, I'll give a brief kind of very overarching history, or not even a history, but just an appreciation for how it can go from a picture shown here on the left, which we like to use just an example of a disgustingly complicated looking optical setup with a lot of mirrors, lenses, filters, and collimation pathways for light to go on, where we get to shrink this down to all being components on a single photonic integrated circuit. You can see on the right there is an example of a Lyonix silicon nitride chip. Lyonix also operates out of the University of Twente, so we share clean room space with them all the time, and they're fun colleagues, and you'll see some collaborations later on in the project with them. But essentially a huge advantage that you get to go with from the left to the right is you get an enhanced energy efficiency, you get increased speeds, you get to reduce the size and cost of a lot of these photonic processes. Of course, this whole thing is far more scalable now, because you can shrink our devices from being a giant table to a whole small chip on the right side. But also it gives us access to a lot of novel functionalities, which I'll be talking about a lot today, because we get to pack in certain materials on top of these integrated circuits, maybe those doped with rare earth ions or enhanced aluminum oxide materials that I'll be talking about specifically. And just kind of a physics picture is we can also think about this as a new paradigm going from fiber optics, where you rely on total internal reflection inside of a cladded waveguide, a cladded fiber optic core in between glass, satisfying total internal reflection, to these nicely compact modes, which can be patterned into planar thin films or planar crystals. And you can see there the electric field overlap inside of a tightly confined aluminum oxide waveguide, similarly surrounded by silicon oxide. Of course, I think this is at the heart of all of my research that I'll be talking about, is that it does take a village. Similarly, with the diverse ecosystem that we have in investigating integrated photonics at Twente, it takes a diverse material landscape to do that. So I'm sorry if you feel like I will be throwing shade at any materials that you might be interested in terms of the bottom right picture being a silicon chip, the bottom left picture being a silicon nitride circuit, and the top two being either on the left erbium-doped aluminum oxide or passive alumina with the UV operation. All in all, it's light going down some tracks, and at the end of the day, we always, from any train station, have a lot of different railways bringing light in, and the application at the heart of it is what's important. So it takes a village, and we like to operate with all of these materials to make the full picture happen and applications get to everybody's home and devices. But at the heart of it, what I'll be talking about today is Alluvia Photonics, a brand new spin-off from here at the Integrated Optical Systems Group, and some research that I've been proud and honored to take part of in its development. And this expands over a lot of those train stations or applications, whether it be LiDAR, industrial processing, biological sensing, AI and datacom being a huge one, since our erbium-doped devices get to operate in the telecommunication bands, or quantum information, which I'll be touching on a little bit with the operation of ultraviolet photonics, which is maybe a new field for many of those in the audience. And I hope to leave you with an appreciation by the end of the talk for what that's all about. So an outline quickly of the talk. I'll give a quick motivation and history into the material, some fabrication and the flavors of aluminum oxide that we work with, some recent work in one of those flavors, polycrystalline alumina, and then you guys with some devices and project applications, which is really the fun stuff at the end of the talk. All of it's fun though. So I love this slide. I use it in all of my talks. I think it's great. You can see there some of the mentioned materials that I've already said, silicon nitride and silicon, and on the left of that, indium phosphide, an extremely popular semiconductor optical amplifying material, which allows the generation of light with electrical contacts. But each of these three you can see in the applicability range, have kind of their own scores or bands that they have transmission at. The band gap of the materials deciding which of these materials can transmit and have the bandwidth of operation for a lot of different applications. You can see silicon nitride reaching into the visible domain, which people like to use for biophotonics and sensing. You can see a big overlap there with the top blue and green bar. Datacom and telecom, of course, being a huge workhorse material, silicon and indium phosphide, providing a whole lot of operation there. And together, these three materials, or sometimes on their own, they can address different parts of these wavelength bands and therefore different applications, depending on what the end devices are. However, aluminum oxide, a material, stretches across all of these bands. So it's an extremely broad band material. It goes below the UV blue operation of silicon nitride and even further into the infrared than all of these materials shown here, up to 5 microns of operation. And on the left there, you can see a picture of an aluminum oxide waveguide that I took in the lab, transmitting, that's 369 nanometers wavelength. So very, very, very small, below that 400 nanometer cutoff of silicon nitride. Whereas it can also be doped with rare earth ions. And these rare earth ions have a high, aluminum oxide has a high solubility for these rare earth ions, which we'll get into. And then these materials, this aluminum oxide, can also be used as a gain material, as a source for this light, which should really make you say to yourself, wow, it's a whole lot of application space and a whole lot of bandwidth that aluminum oxide can operate about. So hopefully you're a little bit excited and motivated to hear what I'm going to tell you about it now. A little bit of a history on aluminum oxide, a nice review paper you can see written here by the co-founder of Alluvia, Ward Hendricks, that it gets to cover a lot of these different transparency windows, whether it's the UV to mid-infrared, has very low propagation losses. Once you start quoting things in per meter, you know it's good. So this is 5 dB, sometimes we'll see here, as low as 1 dB per meter. A moderate refractive index around 1.72 at 1550. It can be wafer level deposited, which makes it very scalable and approachable to clean room technology. As I mentioned, you can pack a lot of rare earth ions in there, maybe in comparison to silicon oxide, where they'll start to cluster and find each other, which happens in an erbium doped fiber amplifier, which I'll show some comparisons to later. As I just mentioned, it's very CMOS, so complementary metal oxide semiconductor fabrication compatible. Clean rooms don't hate this material, essentially, and we can use it in a lot of fabrication devices. We also like to add here that it's highly linear. Some people might see this as a disadvantage, but when you are talking about it as a high power amplifier, you don't want any funny non-linearities to come up. So that's a big advantage of working with aluminum oxide, and therefore it also has high power handling. However, it's not new. For those who know their laser history well, the actual first demonstrated laser was a ruby laser, which is cerium doped sapphire. Sapphire is chemically aluminum oxide. So it's actually has a very rich history in photonics, being the first demonstrated experimental laser. And its naturally occurring state is corundum, which forms very popular gems that stretch way back in history to our well-known early days as humans. So it's been around for a while. And funny that it's popping up so much in geopolitics recently, or not so funny, but they're not actually rare. So the rare earth elements that you see here in this blue circle, erbium you see popping up there, ytterbium, cerium, is even as abundant as a well-known material like nickel. That red on the left-hand side there, so atomic number in the x-axis and abundance in the y-axis. So these rare earth elements, they're not actually rare, but they are only formed through the formation of supernovas, and they kind of get speckled across a rock-forming planet such as ours. So they're sometimes hard to find in small deposits, but they're quite abundant on the planet and are not actually rare. So another fun fact you can take away with you, just like the baby's knees. Why UV photonics, though? To motivate this a little bit, because we're talking about erbium-doped alumina and UV-operable alumina, there's new and exciting applications that are popping up, which Alluvia can really take a corner on as a pure-play aluminum oxide foundry, whether it be UV Raman spectroscopy, which we'll talk a little bit about, white light sources, metrology, quantum ion traps, which I'll introduce a little bit of, and many more application spaces, and let's call them industries and future customers that can benefit from using UV light. But why rare earths? So I'll introduce two slides here that have some fun Venn diagrams on saying why we need to make rare earth ions into amplifiers. Well, they are possible to have, capable to have very high powers while remaining spectrally pure, and can be processed in a very flexible, clean room friendly way. Compared to a semiconductor optical amplifier, however, which are electrically pumped and can have very high gain per unit length, they are made with epitaxy, which is sometimes seen as more costly, but also is not a deficit here, just another different technique. If you compare these to parametric amplifiers, which can achieve very low noise, they rely on nonlinearities and are therefore power limited and have very low pump efficiencies. Essentially takes a lot of pump power to create this parametric amplification. In all of these Venn diagrams for the amplifiers, of course, there are some overlap. The SOAs and the parametric amplifiers are difficult to integrate into single PICs and single systems, are more expensive, and rely on methods such as heterogeneous or hybrid integration. However, the optical pumping is maybe seen as a drawback for certain applications and certain integrations, which I can definitely talk about and address, and maybe some of you will have questions on and later. So the rare earth ions can remain high power, spectrally pure, and can have flexible processing. However, Dawson, some may ask, why do this in aluminum oxide? You can have many different rare earth amplifying materials. As I mentioned already, the power handling in aluminum oxide, because it's linear, is an advantage. The material itself can be inherently low loss. It's very high rare earth soluble, and we can dope it in situ of the actual fabrication for the material. In comparison to silicon nitride, this relies on ion implantation after the fact, where high energy implanters are required, which you can see here in this very nice paper where they got very impressive amplification results in the Kippenberg group. Still relies on ion implantation, which is not done while the film itself is being deposited. I'll talk about that a little bit in the fabrication section of my talk. However, they can have very significant ultra low losses, and as I said, there are made with chemical vapor deposition. In comparison, lithium niobate also been doped with rare earth ions. However, its material has a low temperature budget, and therefore you have a limited amount of claddings or limited choice of the cladding material, which you can put on top of these devices. They rely on doped crystals. However, they're inherently piezoelectric and rely on smart cut technology to form the wafers. Not all of these are exactly drawbacks, just showing an overall comparison. As I said, no insult if you're interested in these materials yourselves. There's some drawbacks, of course, aluminum oxide. It's hard to etch, just like lithium niobate. It can be done though. However, it can be done monolithically and has this linear operation, which lends itself very well to amplification, as I'll show you guys. And kind of what I like to just leave you here with is that integration is the key answer. The fact that all of these Venn diagrams are still justified and why I would pick aluminum oxide is because the monolithic integration is a very huge benefit here when it comes to scaling these devices to not just get tens or hundreds, but millions of these chips made through a foundry clean room. So monolithic is possible with the reactive sputtering. Of course, it still requires heterogeneous pump integration with another 3.5, so we still need 3.5 materials to help ours work. It avoids this high energy implantation from the ion implanters for silicon nitride. Of course, we still need to do some heat treatment, but it can be done because our material has a high thermal budget. And aluminum oxide itself can take a lot of different rare earths, and it's relatively agnostic for in situ doping process, such as sputtering, which I'll show you guys. And we can use solid targets to do so and don't rely on MOCVD or different incorporation methods where rare earths will come in with a lot of ligands and OH bonds, which are not nice in an amplifier. Monolithic, 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 a huge integration benefit. Some examples of the history of different materials, that have been integrated with aluminum oxide, some done by my past supervisor and old groups from this university as well, where on the middle image, you'll see it integrated with a silicon waveguide, where aluminum oxide tapers, silicon tapers to aluminum oxide rib waveguide, where the other images are shown of different fabrication techniques and how to integrate this with silicon nitride waveguide technology. So it lends itself very well to being sputter deposited on a wide variety of materials, or on the right-hand side, top image shows an example of atomic layer deposition done onto very, very tight morphology grooves you can see there. And all of these done in a monolithic manner, which really hits home this point that I'm trying to make about the integration aspects and the advantages of using aluminum oxide. So what's been missing so far? So we have to have alumina capable of a high temperature cladding process, which I'll show you guys polycrystalline aluminum oxide can handle. We need to have a clear benefit of using this material over others. There's a reduction of quenching due to amorphous media that I'll mention, and also standardized processing, which is being done with Alluvia now. So don't worry, we'll be able to fix it, and yes, we can. So here's some fabrication flavors that we do aluminum oxide with. In the past, a lot of work has been done on amorphous aluminum oxide, some more glassy material, which has a lower deposition temperature. However, this lower deposition temperature lends itself to an amorphous material, which has a smaller thermal budget, therefore can't be used with LPCVD, silicon oxide, where you see PECVD in the bottom left image here, does not have low UV losses and has an index of about 1.64. However, when you sputter at a slightly higher temperature in aluminum oxide, you get polycrystalline stage, which does require a higher temperature. Maybe that's seen as a drawback because you can't do back end of line deposition of this material anymore. However, this polycrystalline aluminum oxide has a very high thermal budget, has very low UV losses, and can avoid clustering of these rare earth ions, which, as I mentioned, is a nasty business for erbium amplifiers. We do so by doing reactive sputtering. So I'll bring you guys through a little bit of an erbium-doped waveguide amplifier process flow. We'll start with a substrate being silicon and thermally grown silicon oxide, where we then do an in situ deposition. You can see in that middle image here, which is actually from John Bradley's thesis, you can see 3 different solid purity targets. This one is an example of co-sputtering with erbium ytterbium, and an aluminum target. Well, once we allow that argon and oxygen gas flow to combine in the chamber, we can start to atomically sputter any onto any substrate upside down on the top of the chamber there. And as it rotates, we'll start to deposit erbium-doped aluminum oxide in situ, where both of these in a single deposition step can create a doped waveguide thin film, or a doped thin film for a waveguide technology. After we do some ellipsometry, you can see there we have nice thin thickness and refractive index uniformity. We can grow layers up to a micron thick just based on the etching selectivity of the e-beam resist that we use currently, and measure a lot of these streaks you'll see on the bottom there with a prism coupling technique to qualify the losses in a wafer before we actually structure these into waveguides. And you see there some Rayleigh fits to different propagation losses, whether it's in the blue wavelengths at 451 or red in 633. After we're happy with the layer uniformity and refractive index uniformity, you can see a current state of our deposition allowing losses all the way down to 0.4 dB per centimeter at 377 nanometers. So this is already a picture that if you're familiar with silicon nitride technology, you can look at this and say, wow, there's no way silicon nitride would even operate that because it's below the band gap, and we can see the clear benefit of using this for a UV operation. The UV band gap, actually we've measured down to 170 nanometers. So we still expect some losses as you get down to 260 nanometers, which I'll show you guys as already 4 dB per centimeter. But theoretically, the band gap of our material is very, very high, with a band gap of 170 nanometers being measured by a UV Woolham vase. After we are happy with the films, we'll move on to electron beam lithography, which we use to designate the resist etch masks, which would be simply a resist that is electron beam sensitive. And using reactive ion etching, so a dry etching technique, we can define these very straight, somewhat angled, but very straight enough waveguide sidewalls. You can see there a nice W being patterned and SEM'd in our erbium-doped aluminum oxide. I also mentioned that LPCVD can now be used because our polycrystalline aluminum can handle these high temperatures without failure of mechanical cracking. On the top right 2 corners of this SEM, you can see a little bit, we call these bunny ears of the PECVD cladding starting, but that's far enough away from the waveguide that it doesn't impact the coupling loss. So you see here a nice cross section of a nanotaper where we would couple the light into the side of our device. To convince you guys that this high quality cladding is important, on the left-hand image, it's hard to make out, but you can see the aluminum oxide waveguide peeking out with a little void hat on top of it. This is what happens when we use a non-conformal, low-quality cladding technique, such as PECVD, which does not fill in tight, advanced structures as much. On the right-hand side, if we use LPCVD, which is done at a higher temperature, therefore the material needs a high thermal budget, it allows us to have void-free definition of these nanotapers, which can allow for very low coupling per facet. Paper, if you're familiar with my work on the left, was recently done with Carlos and I, where we got 25 dB coupling loss per facet, which is absolutely awful, where we've now advanced the technology, coming soon to papers near you, where we can show dB losses of about 2 per facet, sometimes even lower than that, using this high quality cladding, which is a huge step forward for the technology. A couple old results here I'll show you of some cross-sectional images of thinner multi-mode waveguides used for ring resonator measurements, brought us down to these passive results of Qs being in the millions now. So once you're in a million Q, you're good for lasers, which is nice for optical amplifiers as well, because the lower the loss, the better. And you can already see here losses going based on old ring resonator fits down to 5 dB, even 3 dB per meter into the L band. So recent work on polycrystalline aluminum oxide. I'll focus, as I have been saying the entire time, on 2 main applications. First, we'll talk about the UV waveguide platform, whereas in the second instance, I'll be talking about rare earth amplifiers with erbium. So some cutback measurements that have been done recently in the past are on a lot of different waveguide widths that you can see here. Things ranging from 550 nanometers to 850 nanometers thick over many different wavelengths shown on the x-axis. Recent results we've been able to measure all the way down for 369 nanometers for a TM mode are at 1.3 dB per centimeter. So that's below the operation wavelength of silicon nitride, where we're already getting losses that are sidewall dominated. So we have to work on kind of smoothing our sidewalls out more to get down to almost that dB per centimeter values. With spirals up to 12 centimeters operating, so about 10 centimeters, quite long devices, so nothing super short that we're extrapolating losses for. These are actually long centimeter spiral devices where you can see different microscope images up on the bottom there for different wavelengths. If you compare this to other materials, you'll see that black line being the silicon nitride absorption limit, which certain groups have really come close to operating near to or even on, really do show the cutoff that silicon nitride can operate into just at that 400 nanometer limit, whereas there are other materials done by MIT with some aluminum oxide, these triangles just slightly higher than our Alluvia platform. Also, the other materials are done with atomic layer deposition, which is again a little bit harder to integrate into different platforms and is more expensive. Nevertheless, they're also very nice materials, and we can see here that the Alluvia platform can really be at the state of the art when it comes to UV losses in waveguide technology. So some upcoming UV work that you can stay poised and excited to see more about are operation at 270 nanometers, so really getting into the UV wavelength. Certain groups are excited for these data on quantum ion traps, which I'll present a little bit later on, and some automated testing to really get our yield numbers locked in, as well as standardized components with PDK development on the aluminum oxide platform. However, bread and butter for my research, I really like to talk about rare earth ions, as you guys have already maybe hopefully absorbed. I'm very passionate about, and I'll touch on some of the ones, neodymium, ytterbium, erbium, and thulium, that have been successfully integrated into lasers and amplifiers on our platform. You can see here, as I said, it's rare earth agnostic. You can almost think of all of these different rare earths as being palettes or paints in a large palette that we can start to structure across many different applications that require this active operation. We've done this with erbium, making aluminum oxide amplifiers. We've done this with thulium, with quite some success for making amplifiers and Q-switch lasers for other groups that I'll show in a bit. Neodymium is a hot one that we're working on currently for O-band operation, which many people are still interested in the data and telecom world. Also, neodymium is something we're also starting to make these really successful. Oh, I showed that twice. Neodymium as a tight gene lasers, because as we all know, neodymium with its 4-level energy system can be done to make very efficient lasers, which is all research we're actively involved in. However, I'll introduce to you guys some really recent results, so you're privy to some data pre-paper, which highlights the excellent performance of our erbium amplifiers, including some gain, output power, and noise factor measurements for 4 flavors of erbium amplifiers, whether it's single layer, monolithically integrated with silicon nitride using the triplex platform that I mentioned, packaged as well, increasing that integration level for new applications, also packaged with pumps, where we're almost at the forefront of what people need in real systems. Just a quick recap that this TOS cladding, so an LPCVD that relies on, I won't go through the whole formulation of the chemical for TOS, but it can allow very, very conformal coating for the tapers, and then these nano sections on the top, SEM that you can see here, to allow low coupling losses. These low coupling losses are also accompanied by low propagation losses. Using simple image analysis, we can extrapolate 1550 in the absorption band and 1640 outside of the absorption band for losses for an amplifier. This is all now for doped devices, where we recently measured background propagation losses below 0.1 dB per centimeter at 1640 outside of the absorption band, which you see there in inset D for very, very low signal powers. That's exciting. Using bidirectional 1480 nanometer pumping, you can see the setup here with 2 pump laser diodes through isolators into a WDMs, which are a fiber in this case. We can bring the optical pump, to the chip, and by shining or shooting a tunable laser through this device, we can measure many different gain wavelengths and powers in the OSA afterwards. Some figures on the bottom there you can see is the the external net gain. So now this is gain that's actually fiber to fiber, so not just gain on the chip, but also gain for the whole system, which is 15 dB in this recent result. With EDFA, so comparing ourselves to commercial fibers, comparable noise, and 60 milliwatts of output power, which is quite high for these devices. We hope that we can also convince you of ways that we're going to increase this to about the 100 milliwatt region. Then we said, you know what, we're really happy with these 30 centimeter devices. You can see here in an image there, but let's crank that design knob up and pump out some 50 centimeter devices, where we've been recently very lucky we've been hardworking and pushing the forefront of these long amplifiers, and are honored to be working with Fix, which is just across the street from us here, to be packaging these devices now using fiber arrays. So another integration level step up, using many channels to access these very long amplifiers for. You can see here that recent results are now very state-of-the-art. External gains of 24 dB with coupling loss of 2.5 dB per facet, really pushing the state-of-the-art for the technology. Now we're at operational gain values that people quote for commercial fibers, with noise factors that are competitive for such devices, with output signal powers on the same scale that I mentioned before, 60 to 70 milliwatts of operation. You can see here a similar setup at the top right image. These also operate across a very large gain bandwidth. So you can see 90 nanometers approximately, which is also just setup limited. We're looking at ways to increase our measurement bandwidth of these devices, with noise figures ranging from 4 to 6 dB in the really wavelengths of interest that people want to operate at. These powers also reaching 24, 25 dB gain across a whole bandwidth is extremely exciting, and we're looking forward to integrating this device into many application systems very soon. Also, a huge hallmark of the platform is that it's temperature insensitive. So there's temperature stability that we've been able to measure, where instead of complete gain roll-off at 80 degrees or 95 degrees, we can see here we only lose about 6.6 dB of gain from room temperature all the way to almost 100 degrees Celsius, where the noise does go down, but at high power, there's essentially no gain decrease or no significant gain decrease for high input powers. This is a nice way to brag to those people who love SOAs, because at least this does not require any heat stabilization. And even when we heat it up, it continues to work, which is exciting for many applications when we talk about wall plug efficiency or applications in harsh environments that might already be at an elevated temperature. Another flavor that I mentioned was this monolithically integrated amplifier, where benefiting from this reactive sputter deposition platform, you can simply, after doing a CMP step and flattening out, done by Lionics, just in our same clean room, we can then deposit on top of the LPCVD cladding our doped aluminum oxide waveguides. Do the same patterning, do some alignment with E-beam technology, and we can adiabatically transfer from the bottom layer to our top layer amplifiers with inline waveguide propagation, and then back down to the nitride to do some advanced devices like WDMs on chip, or really low loss coupling at the edge of the chip itself. So as I said, this is in collaboration with Lionics, done through a project called Ophelia, which has recently ended here at the University of Twente. Now you can see the only difference in the setup is that instead of using two sides, we're using a single fiber array to do the measurements into the device. And we've been able to recently show gain in a similar fashion to the others for a 30 centimeter device, getting to that above 15 or external gain of 15 dB. You can see I have internal gain listed here, but the coupling losses are 1.4 dB per facet. So just at that same kind of gain value has been achieved on top of silicon nitride waveguides, which is very exciting. And you can see here proof with that green spiral, the green diminishing as it goes down to the silicon nitride, with that characteristic glow not being present, of course, in the material that's not being amplified. Some recent results here also just shown. We have an internal NF, so this is without the coupling losses, down to 3 dB. Extremely exciting for applications in data and telecom. We're going to chop these signal up very quickly in something like a telecom transmission measurement, with similar external gain and output powers from the chip. And this is something we're really looking forward to enhancing more in the future. So we've been able to repeat this on top of silicon nitride across the same bandwidth as before, with broadband operation across the C and L band, as well as broadband internal noise figures, which are comparable to EDFAs. So future work in this direction is going to be done on the WDM optimization and enhancing the gain even further. I'll quickly breeze through a little bit of this, but we enhance this one more step further in the Ophelia project to now separate the pumps onto the other side of the chip and package these in a way heterogeneously to allow for a small compact form factor amplifier. So you see there, just in the comparable to a euro coin or just a little bit smaller than a loonie, a free space coupling of the pump with an isolator in line. So you see there the optical pathway going from the Fabry Perot 1480 nanometer pumps on the side across a mirror and an isolator in line to reach the chip, which then allows the chip to be packaged and pumped on a tech with a fiber array polished and packaged in a small form factor, really to the stage where it's useful for applications in many different device fields. Similar gain was achieved for that 15 dB benchmark for this 30 centimeter device, with off-chip powers really meeting the demands of some of our end users here. So this is an extremely exciting project that we are happy to put a nice end cap on. So I'll quickly, for the last little bit of my talk here, as I'll wrap up soon, just show you guys briefly some other devices and project applications that we've been working on. As I mentioned, we've been excited to do some UV Raman spectroscopy, as well as ion traps with ETH Zurich for quantum computing demonstrations, really utilizing this UV wavelengths. With epoxy-free attachment, also done by Fix here, you can see that we don't have any of these polymers in line of the UV light, which a lot of polymers absorb, so we can still do the packaging here. And we are even stuck in the lab saying, well, we're now doing all these UV photonics where there's a lot of less components available, such as fiber optic splitters at 369. So we made them ourselves. We are able to utilize the waveguide technology to say, okay, well, if we need splitters, let's just make splitters on chip and then couple them with these arrays. And we can already get an appreciation for the application space that we're able to achieve now with the UV photonics. Similarly, the waveguide enhanced Raman spectroscopy was a huge project that we've been working on with a company called InSpec, which gets to ignore the autofluorescence of the material itself and have a very, very low background signal to make these extremely sensitive waveguide enhanced Raman spectrometers, which we're currently working on and making as we speak, actually, to get these enhanced Raman sensitivities. Both of these have some kind of challenging technology cross sections that we're hoping, not that we are achieving, with sensing windows opened up on our platform, as well as decharging and charging layers for those enhanced quantum traps, where they really care about the electric field of the ion on top of the chip not interacting with the contacts below. And these are an enhanced, and sorry, what do I want to say? Advanced technology cross section that we're able to achieve on our platform, which is in due part to the flexible processing that I mentioned at the beginning of the talk. You can see here wafer bonding, also done by Fix, so they can address all of those ions as they'll float on top of the chips, which I invite you to stay in tune with the Alluvia project and see the benefits that we'll bring there. We also have Mach Zehnder modulators so far, just with thermal phase shifters, which we're enhancing with aluminum nitride soon. And we can have a lot of enhanced benefit from using a PDK available through Lucida to standardize all of our components so that designers can use them more and more around the world. These designers can jump on the Alluvia platform in two manners. We have offered MPW runs. So if you go to Alluvia Photonics, a shameless plug at the link there, you can join our next upcoming multi-project wafer runs and hop on one of our wafers to test your devices. And we're also allowing pre-orders of these erbium-doped waveguide amplifying qualification kits to see if you guys need erbium-doped amplifiers inside of your systems. These have been used already by many of our exciting collaborators to achieve some external cavity tunable lasers at 400 nanometers, which got state-of-the-art side mode suppression ratios and output powers for this wavelength, as well as an absolutely bananas amount of power from this group in the femto chip project using thulium as a dopant to achieve temporal and amplification output powers of 800 watts inside of these devices, where you can really now appreciate the power handling capable of aluminum oxide shown here. I invite you to look into these projects separately to keep up to date with them. We also quickly now, I can just show you really briefly, we've tried to do 4-wave mixing in the devices almost just as a damage threshold to see if the devices would blow up and could investigate that N2, where we had 50 watts of CW inside of a ring. And we have ongoing characterization in this to see that the material is very also inherently linear. And supercontinuum generation, also hard to achieve, but still possible with a non-optimal waveguide geometry, which we're looking into investigating also in the future. So with that, I hope I've left you just to summarize a couple important points that for certain things, aluminum oxide is, in my opinion, the best option for a couple different applications. It's a disruptive material for the UV photonic world, being the only one available for photonic integrated circuit manufacturing. It's a very effective host material for rare earth dopants due to that solubility and a couple other reasons. Monolithic integration, high power handling, and a high thermal budget, and it's poised for system integration. So if you guys have exciting experiments, you foresee aluminum oxide being able to fill holes in your application gap, please reach out at that email below and reach out to Alluvia Photonics. We can see how we can work together to shine the most light on both of our experiments, no pun intended. So with that, I'd like to acknowledge, of course, many different industrial collaborators and research groups, as well as a very bright, energetic, and fun team to be a part of here at the Integrated Optical Systems Group at the University of Twente. And I welcome any questions and thank you for your kind attention for this webinar. And thank you very much also, David, for the coordination.
No, thank you. That's all I can say is you've been busy. Thank you for the wonderful presentation. We've definitely got a load of questions. I don't even know if we're going to have time to get to my questions, but I think yeah, let's get started. So this question came in around slide 25, 26, somewhere around there. So the question was. I'll wait for you to get to the slide just in case, but
okay.
can you
ask it as I flip? Yeah.
Yeah, so can you explain what monolithic means in this context? Does the waveguide behavior not depend on index of refraction of adjacent materials, so there is no core-clad relationship?
No, there's definitely a cord-clad relationship. It does have overlap with the surrounding materials, but when we talk about monolithic in this approach, we're really just meaning that there's no hybrid or heterogeneous integration of the material that's required. So it's, I think this is a nice definition by Roll Bates. Monolithic just needs one wafer. So I'll put my hands up and say that's the answer to that. Monolithic is one wafer, heterogeneous is multiple wafers, hybrid is multiple chips. So in this manner, we can use one wafer and stack these materials on top of each other, which is cheaper.
So this next question comes from a colleague of yours. I won't dox anybody during this talk, but it says, "Great talk, Dawson." Two-part question is there a specific reason you use EBL, I assume electron beam lithography, for the writing step? And can you replace EBL with something more scalable, such as photolithography or nanoprint lithography? This one came in around slide 35.
Yeah, so maybe not nano imprint at this stage, but definitely when we're talking about scaling up to standardizing the platform, E-beam is not as is more flexible as we're working with the platform and the clean room that we currently have. So as we move to more medium and high volume fabrication, if we can get down to a very expensive litho stepper that can do these 200 nanometer tapers, then of course we can standardize to a more manufacturable, high scale technique such as masked stepper lithography. But these nano tapers that I'm showing here for these devices, you can see the scale bar there are 200 nanometers. So in our clean room, that's just more readily available to do with E-beam. Eventually, one day with a lot more money and standardization, we can do an immersion lithography stepper. So there's no inherent roadblocks there. Good question.
Makes sense.
One day that will have to happen, yeah, to make millions, of course, of these devices.
Of course, that's always the goal, always millions.
Yep.
So the next question came in around, actually, this was more of a general question. So thanks for the interesting talk, of course. Can you address the level of roughness possible with the material in particular for working with UV? And is such a level easily achievable, or are special processes required?
That's a really good question. First off, as you see on this slide, I have TE and TM loss results, and they differ drastically for the same waveguide width and wavelength. And that's because the sidewall roughness, this Rayleigh scattering, scales by lambda over 4, which is such a problem in the UV realm. So currently, because we just use E-beam resist as the etch mask, we're inherently a little bit limited to our knobs that we can turn for the sidewall roughness reduction. This is why we're looking at using and moving towards hard mask etching. And this hard mask etching can inherently kind of pass less of this roughness to the next layer, that being the aluminum oxide, which is hard to do, right? So the answer to that is we're working on hard etching to kind of address this. And something that Ward always likes to say, the CTO and co-founder of Alluvia, is sidewall roughness is money. So as we scale up to more manufacturing techniques, we can look at advanced processes to reduce the sidewall roughness. But mainly my quick answer is moving towards hard mask etching rather than soft mask etching, which we're currently using. But it's the biggest, I think, hurdle that we need to address for working in the UV, for sure.
Mm-hmm. And there is sort of a second part to this question. Does special attention need to be paid to the cutting, polishing, and machining processes with chips and waveguides compared to other materials?
I don't know if it'd be compared to other materials. All of this scattering is more prevalent in the UV. We definitely, for almost all of these UV chips, polish the facets now. So we use a polishing machine to really polish the facets. And we're really also looking at using, and we do this, and the development is ongoing, use CMP on the top of the aluminum oxide layer. So even just to reduce the inherent roughness of the top deposited layer, we also use CMP to reduce that. It might be worth it to look at wet etching to flash smoothen some of the actual waveguide sidewalls, but that's not done yet. but for sure, the polishing on the end facets is required. We see a reduction there from about 15 dB. Let's say it's at 405 nanometers. Just recently, I was measuring chips at 405 nanometers. We saw 15 dB coupling losses per facet, which is huge. I gave them to Nadia, a coworker that's heavily involved in the patterning, and she was able to polish them. And we brought that down to 5 dB per facet. So polishing can make a whole almost 20 dB power budget save when it comes to polishing the coupling regions.
Mm-hmm.
Yeah, extremely important.
Yeah, very cool. And actually, as a quick add-on to that question, with the sort of inverse taper couplers that you design, do you feel like those are more sensitive to the polishing quality or less sensitive than something like a just bare cleaved waveguide?
I'd say that's something we haven't done in the UV yet. So actually, we're not sure. I'd say it's maybe less inherent because you can get a little bit of a win on having a really long interaction length with these adiabatic tapers. And if you design them right, they don't, at the UV, they will be just sidewall dominated, not facet coupling dominated. So it's also another reason why it's really cool that if you love the low loss coupling of silicon nitride at the facet edges, then throw that beneath the aluminum oxide and you can benefit from having really low facet coupling there with high quality and integration heritage. And then, I didn't show it here, but we had chips that just went from silicon nitride to aluminum, back to silicon nitride, back to aluminum through multiple tapers. We do like a cutback approach, and we were seeing losses of 0.1 to 0.3 dB per transition. So we can get quite low with this as long as we don't need to do hundreds of transitions, which you would design around, of course.
Yeah, that is very impressive, and I assume you only need to use a couple of those transitions in a simple system, right?
Ideally, yeah.
Another question that came up, and this is probably, especially with the higher power amplifiers that you're using, is how much heat comes out of these devices, and what are the challenges with handling it, if any?
We actually haven't seen any thermal challenges yet. It's extremely maybe prevalent on the thulium stuff that I was showing at the very end where they were doing pulsed operation. They did have some failure of the material. I don't want to speak too much for them because I didn't do these measurements, but all of their failure was in the silicon nitride, not the aluminum oxide. We know ruby and sapphire is one of the most robust chemically and mechanically hard materials known to mankind. And so it's extremely thermally insensitive. And I think these measurements that I was showing of the thermal operation where we get really, really low differences in the gain as we heat up the devices is kind of a hallmark of this point where we don't really have a lot of thermal problems. I mean, as I mentioned, we don't cool the chips as we pump them, right? And if people are out there in the SOA world, shake their fist at because they'll have to have their devices on a heat sink and be cooling them actively on a tech while they do their gain operation, which we don't need to do.
Mm-hmm. Yeah, that is, I think, an extremely impressive result, especially since I remember melting a piece of tape that one of my silicon chips was mounted to by using one of the micro heaters, but I think I was putting a little too much power through that.
No two-photon absorption here, so really, really low thermal issues.
Yeah, very good point. So this next question, I think it's a good question because it's also partly a question that I want to ask. Are there electro-optic phase shifters possible or realized in a rare earth doped aluminum oxide? And what are the pros and cons?
So I'd say a quick no, right? We're trying to see if this can be possible with the aluminum oxide, but we think we would need absolutely high powers and kind of silly things to do this because the centrosymmetry is not there for them, which is why Alluvia is also strongly pushing development on aluminum nitride. Right? So for these electro-optic phase shifters, we're going to rely on the compatibility and the fabrication techniques to put different materials with ours, right? So aluminum nitride, we're just switching out the reactive gas from oxygen to nitrogen. And then we can also monolithically sputter aluminum nitride on top of the devices. And with these adiabatic transitions, do the electro-optic modulation somewhere else and bring it back down to the aluminum oxide layer. So unfortunately, there might be some interesting things in the future that people can do with the dopants inside of them to be electro-optically active. But this is something that I would say is further down line in the future and is not our specialty. We're looking at aluminum nitride for this.
Fair enough. And in the material itself, is there anything like a strong stress optic coefficient, perhaps?
Not that I'm aware of. And now, actually, that I just answered that last question, we're also looking at BTO for the infrared for integrating this on top of. But the stress optic coefficient is what I could imagine might be useful with a lot of rare earths, right? So if we really, really pack rare earths where we're not trying to use them now for optical amplification, but trying to use them for something else, which are limits that we haven't really seen yet, that could be an interesting field to explore.
Mm-hmm. All right, so there's no shortage of questions here. We're
Good.
Definitely not going to get to mine, even though, yeah, I've been sliding them in here. So
Nice.
what is the meaning of EDWA compared to EDFA and micro EDFA?
So that's just the W being switched out from waveguide to fiber, right? So micro EDFA can get quite small. These have really tiny bends, and they can pack them into small boxes. But the EDWA is an erbium-doped waveguide amplifier compared to the erbium-doped fiber amplifier. I'd say I don't want to say that we're competitive with 3.5s yet, although I do personally see that happening eventually. We, of course, need them for pumps. But the micro EDFAs are an exciting competitor that we can finally step into the ring with. Well, they say, okay, we can pack them such smaller. But if you've been to a EDFA factory, it's still humans sitting there bending these fibers into boxes. And I don't want to say it's dystopian or something, because I know that's probably a fulfilling job, but these can be done millions and millions on a wafer scale. So eventually the cost benefits, even if we're not as small or not as efficient as the fibers, we can still really enhance the doping concentration in alumina, which we haven't explored too much of, and mass produce these in a wafer scale technology.
Mm-hmm. Yep, definitely exciting. Next question. We're going to go rapid fire now.
Yep.
What is the lowest wavelength in the UV operation that you've seen in the Illumina waveguide platform?
That's the 265 that I was mentioning. So the band gap is one. Yeah, we're at a limit of sources. You know, not many people make these lasers that go much below that. So if we want a diode laser that's fiber coupled, 265 is what we've measured. But the band gap has gone down to 170 in the UV phase. So we're hoping if people come out with new lasers, we can test them in our picks.
That's a good problem to have, to be laser limited by your material.
Exactly. Yeah.
For certain UV wavelengths, is the aluminum oxide waveguide single mode?
Yes, and that's another important point of us doing this kind of width variation that I was showing for the UV losses. Oh, it's a bunch of different slides, and we'll get there. But that's exactly why for some wider widths, we had lower losses, because those were multi-mode, and the fundamental mode touches less of the sidewalls. But for some of those 369 nanometer loss values, those were single mode waveguides.
Mm-hmm. Gotcha.
But that's also why E-beam's needed, because those have to be so narrow now to get single mode condition.
Right, yeah. This last question here says, thank you for the presentation. Did you try to test these chips at 1550, and could we apply these waveguides to stimulated Brillouin scattering applications?
Yeah, so the only, of course, almost all of the erbium results that I'm showing here were at 1550. And stimulated Brillouin scattering is something that I was saying David Mariupong does a lot with here. The only problem there is this is a very hard material. So the phonon energy is very high. So if you're familiar with SBS, you know you want a softer glass, such as tellurium dioxide or silicon nitride, which are both two good candidates for that. So I'd say stay away from aluminum oxide if you want SBS, but that remains to be seen. But that's my quick answer for that is for Brillouin scattering at 1550, don't go with a high phonon energy like this.
Fair enough. Okay, and this last question. So yeah, we only have really time for one last question. And I'll give you maybe a couple of 2 to 3 minutes to answer this if you want. But for those who are sort of unfamiliar, you know, what exactly is the interaction between something like the host material, the aluminum oxide in this case, and the rare earth? How do those two play together? Is the rare earth dopant even chemically bonded in that case, or is it sort of interstitial, all that stuff?
It's a really good question, because at the beginning, I was showing amorphous, which was actually a lot of my past research was on amorphous aluminum oxide. And now when we're talking about polycrystalline aluminum oxide, you want to start to imagine that the erbium has to sit in certain sites, right? And these certain sites are not crystalline, they're polycrystalline, because if you have crystalline aluminum oxide, the erbium is no longer ionized inside of it because of this symmetry gets completely there. Symmetry is there. And for an ionized rare earth, you need non-centrosymmetric host materials. So when you want a non-centrosymmetric host material, your choices become a little bit more limited, but you can avoid things such as nonlinear broadening by using an amorphous medium, because the cloud around it of aluminum oxide gets to kind of muddle the different broadening mechanisms that you would get in a laser, right? So amorphous sea of alumina, you'll find little erbium ions in there, which can also therefore move around easier and cluster with each other, which is what we hypothesize and speculate is a big reason that this polycrystalline material is a little bit better than the amorphous alumina. We can get lower losses with it as a bare host, but these erbium sites that are inside, we do some preliminary XRD measurements to measure this crystallinity and kind of see how also heat treatment can affect the host material. It's a very delicate interplay. This is a very good question. And if I wasn't in such a application-specific hardcore gain measurement phase, I would have spent my time here at University of Twente doing this kind of delicate spectroscopy, XRD, high-resolution TEM images to see these sites and kind of tease out where they're sitting in the host material. But this is the next frontier of science. Now that we've proven the material is interesting for applications, we can step into the cleaner and more and investigate this exact material science to see the interplay of those erbium sites not clustering inside of a more defined polycrystalline alumina host. So stay tuned for that, and I hope one day we'll be able to answer that question with a little bit more data. But those are all just my feelings and hypotheses for now.
Yeah, the work never ends, but you guys have made some tremendous progress. I think this is all very exciting stuff. So I believe that is all the time that we have for today. I'd like to thank Dawson again for his presentation. You'll be able to view this webinar and all of our upcoming and previous webinars on our website at thorlabs.com/webinar. Sorry, webinars. Thank you very much for your attendance, and we hope to see you again. Thanks again, Dawson. Appreciate it.
Thanks a bunch, David, and thank you all for the great questions. I look forward to coming to more of these webinars. So thanks a bunch.
Thank you.